But when you look into the night sky, you think you're looking out. You're not. You're looking back. Back through time. Back through light that left its source before Earth had oceans, before the sun existed, before even the Milky Way had fully formed, and when the James Webb Space Telescope unfolded in the cold silence beyond Earth's atmosphere, it was built for one purpose: to look deeper than anything ever had. Deeper means older. Older means closer to the beginning. But something happened when it stared into that ancient darkness. It didn't find what we expected. It found galaxies that were too massive, too organized, too mature at a time when the universe should have been chaotic and newborn. According to everything we thought we knew, those structures shouldn't exist. Yet there they were, bright, structured, impossible, which means one of two things is true. Either the universe grew up much faster than physics allows, or our understanding of the beginning is incomplete, and if that's true, then you are living inside a story whose first chapter might be wrong. What James Webb saw isn't just distant light. It might be evidence that the early universe was not what we were told. And once you see it, you can't unsee it, because the deeper we look, the less certain the beginning becomes. The telescope itself doesn't look dramatic. Folded gold mirrors, a shield the size of a tennis court, floating quietly nearly 1,000,000 miles from Earth at a gravitational balancing point called L2. But inside that silence, it is doing something radical. It is collecting infrared light so ancient that it has been stretched by cosmic expansion into wavelengths invisible to human eyes. Light that began its journey 13 billion years ago, when the universe was only a few 100 million years old, barely 2% of its current age. Before James Webb, our best images from Hubble showed faint smudges, early galaxies forming slowly, clumsily. That matched our model. After the Big Bang, the universe was hot plasma, then cooling gas, then gravity slowly pulled matter into stars, then galaxies. It should have taken time, a lot of time. Structure requires patience. Gravity is not hurried. But when Webb focused on a tiny patch of darkness, a region no larger than a grain of sand held at arm's length, it revealed thousands of galaxies. Not small ones, not barely forming, massive, bright, spiraled, structured. At a time when they should have been infants, they looked grown. Astronomers ran the numbers again and again. The redshifts were correct. These galaxies were truly ancient, which created a problem. Because if galaxies that large existed that early, then either matter clumped together far faster than our models predict, or something fundamental about the early universe is missing. This wasn't a small adjustment, it was a structural crack, and cracks at the foundation matter. The standard cosmological model lambda CDM predicts how matter should evolve from the Big Bang to today. Dark matter scaffolding, gradual merging, hierarchical growth. But Webb's deep field showed galaxies with masses equivalent to the Milky Way when the universe was barely 500 million years old. That's like finding a fully grown forest where you expected seedlings. The universe wasn't supposed to have enough time. Time is the limiting ingredient. Stars need cycles, galaxies need collisions. Heavy elements need generations of supernova. And yet, there they were, fully luminous, fully structured. Some scientists suggested we were miscalculating their mass. Others proposed bursts of rapid star formation. Some whispered about exotic physics, early dark energy, modified gravity, primordial black holes seeding rapid growth. But none of those explanations feel simple. And in science, when the simplest model begins to strain, you pay attention. Because this isn't just about distant galaxies. It's about the timeline of everything. If galaxies formed faster, what else happened faster? Did reionization begin earlier? Did the first stars ignite differently? Was inflation slightly different than we assume? Or, and this is where it becomes unsettling, is the Big Bang model incomplete? Not wrong, incomplete. There's a difference. Throughout history, our understanding of the cosmos has repeatedly shattered. Earth was the center. It wasn't. The Milky Way was the whole universe. It wasn't. The universe was static. It wasn't. Each time we looked deeper, certainty dissolved. Webb may be the next dissolver. But this is only the first layer, because the deeper data, the spectral fingerprints, suggest something even stranger. Some of these early galaxies contain surprisingly heavy elements: carbon, oxygen, nitrogen, elements forged inside stars. But stars need time to live and die to create those. So either the first stars were unbelievably massive and short-lived, or star formation began earlier than we think, which pushes the cosmic dawn further back, closer to the beginning, uncomfortably close. And when you push that timeline back, something compresses. Because we believe the first few 100,000 years after the Big Bang were a fog of plasma, opaque and chaotic. Then came the cosmic microwave background, the afterglow we can still detect today, a snapshot of a baby universe. But if structure emerged too early, what does that imply about those first moments? Were density fluctuations stronger? Was dark matter behaving differently? Or is there physics before inflation that left fingerprints we haven't interpreted correctly? And here is where the stakes quietly rise. Because the Big Bang isn't just a theory of explosion, it's the origin of space, time, energy, and physical law. If its early evolution shifts even slightly, our understanding of everything that followed shifts with it, including you, your atoms, your existence. The elements in your body were forged in stars, stars that formed inside galaxies, evolved over billions of years. If that timeline changes, the chain of causality shifts. Webb didn't just photograph galaxies, it photographed assumptions, and some of them look fragile. But the story goes deeper still, because what Webb truly uncovered is not just older galaxies. It is a growing sense that the universe may have been born with more structure than we thought possible. And if that's true, then the beginning wasn't simple. It may have been intricate from the start, which raises a haunting possibility. What if complexity is not an emergent property of time, but a fundamental feature of reality? And if the universe began complex, what does that mean about what came before? Because every answer we find at the edge of time seems to create a deeper question behind it, and James Webb is still looking, deeper, longer, into a darkness that may not be empty at all. The next layer of this mystery doesn't just challenge timelines, it challenges the concept of beginnings. And once we step into that territory, we are no longer just studying galaxies. We are confronting the limits of explanation itself. And that's where the real shock begins. The first shock was visual, the second is mathematical. Because once the initial images stunned the world, the real work began: spectroscopy. Not pictures, but fingerprints. Not beauty, but evidence. James Webb doesn't just see galaxies, it dissects their light. Every atom absorbs and emits light in specific patterns like barcodes, written across the spectrum. Hydrogen leaves one signature, oxygen another, carbon another, iron another. When that ancient light reaches Webb's gold mirrors and travels through its instruments, it splits into data, and that data tells a story. And the story it began to tell was deeply uncomfortable. Some of the earliest galaxies, those existing only a few 100 million years after the Big Bang, weren't chemically primitive. They were enriched. They contained elements that require previous generations of stars to live and die, which means before these galaxies formed, something else had already burned. Pause there. If you compress the entire 13.8 billion year history of the universe into one calendar year, the Big Bang happens at midnight on January 1st. On that scale, the first billion years occur in the first few weeks of January. Webb is seeing galaxies that look mature before mid-January. But enrichment, the buildup of heavy elements, should take longer. It requires stellar life cycles. Massive stars forming, fusing hydrogen into helium, then into heavier elements, then exploding as supernova. That explosion spreads enriched gas into space, which then collapses again to form new stars. It's a process of recycling. Recycling takes time. Yet Webb's data implies this recycling had already happened, rapidly, intensely, almost immediately. Which introduces a possibility that sounds subtle but is enormous. The first stars may not have been like the stars we see today. Astronomers call them population. The third stars, hypothetical, primordial, composed almost entirely of hydrogen and helium. No metals, no complexity, massive, violent, short-lived. We've never directly observed one, but Webb may be seeing their aftermath. And if population, the third stars, were far more massive than we imagined, hundreds of times the mass of our sun, they would have burned fast and died explosively within a few million years. That could accelerate enrichment. But here's the tension. To create the number of heavy elements Webb is detecting, you don't just need a few massive stars, you need a lot of them, which implies star formation ignited explosively across the early universe, not gradually, but almost everywhere at once. Imagine a dark cosmic ocean suddenly lit by millions of supernovae, not flickering, igniting. That is not the slow hierarchical growth many simulations predicted. That's something closer to a cosmic surge, and when models were rerun with Webb's data included, the simulations struggled. Some galaxies appear too bright for their estimated mass, some too massive for their age. Some show disk-like structures, organized rotation far earlier than expected. Structure is not trivial. To rotate smoothly, matter must settle, turbulence must dampen, gravity must sculpt. But these early galaxies don't look like chaotic clouds. Some look orderly, and order implies stability. Stability implies time. Time is what we thought they didn't have. So either our estimates of cosmic age at those redshifts are slightly off, or the universe formed structure faster, or something in the dark sector, dark matter, or dark energy behaved differently in those first few 100 million years. And that possibility is where the narrative deepens, because dark matter is the invisible scaffolding of the cosmos. It outweighs normal matter 5 to 1. It doesn't emit light, it doesn't absorb light, it doesn't interact electromagnetically, but it pulls. And that gravitational pull allows gas to collapse into stars and galaxies. If dark matter clumped faster than predicted, if its density fluctuations were stronger, if its properties weren't perfectly cold and collisionless as the standard model assumes, then galaxies could assemble earlier, which means the problem may not be with visible matter at all. It may be hidden. Some physicists are now revisiting early dark energy, a temporary phase where dark energy briefly influenced expansion differently than today. If the expansion rate changed slightly in the early universe, timelines shift, not dramatically, but enough to alter when structure forms, and small changes in cosmic parameters ripple outward. The cosmic microwave background, the oldest light we can see, was measured precisely by missions like Planck. Those measurements anchor our cosmological model. But if Webb is hinting that something was off in the early expansion history, then even that anchor may need reinterpretation, not refined. But refinement at this level is seismic, because cosmology is a tightly woven web. Change one thread, tension shifts everywhere. And then there's something even stranger. Some Webb observations suggest that supermassive black holes may have formed astonishingly early. Black holes millions of times the mass of the Sun. At epochs when the universe itself was barely emerging from darkness. Black holes grow by feeding. Feeding takes time, unless they were seeded differently. Primordial black holes, hypothetical relics formed directly from density fluctuations shortly after the Big Bang, could bypass normal stellar collapse. If they existed, they would rewrite the opening scene of cosmic evolution. Suddenly, black holes wouldn't be endpoints of stars, they would be primordial architects. And if early galaxies formed around these massive seeds, that could explain rapid organization. But now we are in territory that feels almost mythic, because primordial black holes blur the line between cosmology and particle physics. They connect quantum fluctuations during inflation to astrophysical structures billions of years later. It's as if tiny ripples in space-time during the first fraction of a second determined where galaxies would later ignite. And if Webb is indirectly pointing toward that connection, then we are seeing fingerprints of physics at 10:35 seconds after the Big Bang. That's not looking deep, that's looking back to almost nothing. Yet here's the none of this proves the Big Bang is wrong. What it proves is that the early universe may have been far more dynamic than our simplified story suggested. We often describe the beginning as smooth, tiny fluctuations growing gently over time. But what if it was violent in ways we underestimated? What if gravity sculpted faster? What if star formation erupted like a chain reaction? What if complexity was seeded almost immediately? There's a philosophical shift hidden here. We tend to imagine order emerging from chaos slowly. But what if chaos was never dominant? What if the initial conditions already contained the blueprint for structure embedded in quantum fluctuations stretched by inflation? Inflation itself, that rapid exponential expansion smoothed the universe, while imprinting tiny density variations. Those variations became galaxies, but inflation is still theoretical. We infer it. We haven't directly observed it. If Webb's data nudges inflationary models in new directions, that affects how we understand the very first moment of cosmic time. And here the tension returns to you, because your existence depends on a delicate sequence: slightly stronger gravity and stars burn too fast, slightly weaker and structure never forms. If galaxies formed earlier than predicted, that suggests the parameters of the universe may allow structure more easily than we thought, or it suggests we misunderstood the threshold entirely. Both are profound. Either the universe, B, is more efficient at building complexity, or we misjudged how complexity begins. And there's one more layer. When Webb stares into these deep fields, it's not just seeing ancient light. It's seeing light that has traveled for over 13 billion years, stretched by expansion, redshifted into infrared. That stretching is measurable. It tells us how fast the universe has expanded over time. But there's already tension in those measurements, the so-called Hubble tension. Different methods of measuring cosmic expansion give slightly different answers. It's a small discrepancy, but persistent. And persistent discrepancies in physics are where revolutions begin. If Webb's deep observations refine expansion rates at extreme distances, they could either ease that tension or amplify it. And if amplified, we may be forced to reconsider our model of cosmic acceleration driven by dark energy, which means the mystery isn't confined to the past, it stretches forward. Because if early expansion behaved differently, the ultimate fate of the universe might shift too. So what began as Webb found galaxies too early is evolving into something far larger. It's a cascade. Early galaxies: right arrow star formation rates, right arrow heavy element abundance, right arrow black hole growth, right arrow dark matter behavior, right arrow inflation, right arrow expansion history, right arrow cosmic fate. Every layer connects, and every layer is now being re-examined. But here's the psychological twist. When humanity first realized the Earth wasn't the center of the cosmos, it felt destabilizing. When we learned the universe was expanding, it felt shocking. Each time the scale grew. Now the scale is temporal. We're not just adjusting where we are, we're adjusting when structure truly began. If the first billion years were more intense, more luminous, more organized than we thought, then the cosmic dawn wasn't a gentle sunrise. It was an explosion of architecture, and we are only beginning to map it. James Webb hasn't answered the question of the beginning. It has multiplied it, because the deeper it looks, the more it suggests that the early universe was not a simple, dark prelude. It may have been a rapid construction site, stars igniting, black holes forming, galaxies assembling at astonishing speed. And if that is true, then the standard timeline we've carried in textbooks may be missing chapters, which leads to a final, unsettling escalation. If structure appeared earlier than expected, then the boundary between beginning and after may not be as clean as we assumed. Maybe the early universe wasn't a blank slate gradually filling in. Maybe it inherited something, some initial asymmetry, some pre-inflation imprint, some deeper layer of physics we haven't yet uncovered. Because when you push your instruments close enough to the edge of time, you don't just see distant objects. You start seeing the limits of your own explanations, and Webb is still collecting light, which means the next dataset could sharpen this tension even further. Not, just challenging how galaxies formed, but challenging what we mean when we say the beginning. And that's where the story turns from astrophysics into something much more radical. There is a moment in every scientific revolution when the data stops being just data. It becomes a mirror, and in that mirror, we don't just see the universe. We see the limits of our imagination. James Webb was built to confirm a story, refine it, add detail to the first billion years after the Big Bang. Instead, it has done something more dangerous. It has made the beginning feel unstable, not shattered, but permeable. And once the beginning becomes permeable, everything downstream becomes negotiable. Because here's the deeper layer hiding beneath early galaxies and heavy elements. Our model of the universe assumes that simplicity came first, a hot, dense, nearly uniform plasma, tiny fluctuations, gradual amplification, structure emerging slowly from near uniformity. But what if near uniformity is an illusion of scale? From far away, the ocean looks flat. Up close, it's turbulence. The cosmic microwave background, our baby picture of the universe, looks smooth to 1 part in 100,000 Darrow. But that 1 part is everything. Those fluctuations are not random noise. They are encoded structure. And inflation, that rapid expansion in the first fraction of a second, is thought to have stretched microscopic quantum fluctuations to cosmic scales. Quantum noise became galaxies. Think about that. Subatomic, amplified into stars. If Webb is hinting that structure formed earlier and more efficiently than expected, it may be telling us something about those initial quantum fluctuations. Maybe they were slightly stronger. Maybe their distribution wasn't perfectly Gaussian. Maybe inflation wasn't as simple as the textbook diagrams suggest. And if inflation shifts, then the very first moment shifts. Because inflation is not directly observed, it is inferred. It elegantly solves several cosmological puzzles: flatness, horizon, homogeneity. But there are dozens of inflationary models, different potentials, different fields, different dynamics. We chose the simplest one because it fit the data. What happens when new data strains that simplicity? Possibility 1. The universe expanded at slightly different rates in its earliest epochs than we assumed. Possibility 2. Dark matter interacted, however weakly, in ways we haven't modeled. Possibility 3. Black holes formed directly from primordial density spikes before stars even existed. Possibility 4. The Big Bang was not the absolute beginning. And that is where the ground quietly disappears beneath your feet. Because when we say Big Bang, we don't mean explosion. We mean the earliest moment our physics can describe. A boundary, a horizon. But horizons are not walls. They are limits of visibility. Webb is not seeing before the Big Bang. It can't. But it is tightening constraints on what must have happened. But now, immediately after, and if what happened immediately after is more structured, more accelerated, more efficient than expected, then the conditions that preceded it may have been more complex too. There are cosmological models, once fringe, now reconsidered more seriously, that describe a pre-Big Bang phase: bounce cosmologies, cyclic universes, quantum gravity transitions where a prior collapsing universe rebounded. In some loop quantum gravity models, space-time itself cannot compress infinitely. It bounces. In certain string cosmology scenarios, our universe could be a brane collision in higher dimensional space. These ideas are speculative, but here's the shift: they are becoming less philosophically distant. Because if early structure feels unexpectedly mature, it hints that the initial conditions weren't random simplicity. They may have carried memory, and memory implies continuity, not necessarily of matter, but of structure. Now imagine this: the universe begins not as a blank page, but as the next page in a longer manuscript. You wouldn't see the previous chapters directly, but their influence would shape the opening lines. Subtle asymmetries, biases, preferred scales. Webb's observations of unexpectedly early galaxy formation don't prove this, but they nudge us toward asking whether the first chapter was truly chapter 1. And then there is the philosophical escalation. We tend to imagine time as linear and absolute, beginning right arrow evolution, right arrow future. But at quantum, P's differently. Near singularities, our equations break. General relativity predicts infinities at t equals 0, but infinities in physics are warning signs. They signal incomplete theory. We have never unified general relativity with quantum mechanics. The Big Bang sits precisely at that boundary. So when Webb shows us that 500 million years after the Big Bang the universe was already bustling with structure, we are forced to re-examine how quickly order can arise from quantum foundations. And here is the quiet shock. Maybe order does not arise. Maybe it is fundamental. Consider mathematics. The laws governing gravity, electromagnetism, nuclear forces, they were already in place from the first fraction of a second. Constants precisely tuned, interactions precisely defined. If early galaxies assembled faster than expected, perhaps the universe's capacity for structure is deeper than we assumed. Not fragile, not barely sufficient, but abundant. That realization flips a narrative. Instead of life and complexity being improbable late accidents in a cooling cosmos, perhaps complexity was latent from the first breath of expansion. Perhaps the universe leans toward structure, And if that's true, then consciousness eventually emerging on a small planet around an ordinary star may not be an absurd anomaly. It may be a continuation of an intrinsic tendency. Webb doesn't detect consciousness, but it detects early architecture, and architecture implies rules that a pattern. But there's a darker possibility too. Some physicists argue that our interpretation of Webb's early galaxy masses may be biased. If early stars were extremely bright and top-heavy in mass distribution, we might overestimate galaxy mass, meaning the galaxies aren't impossibly massive, just unexpectedly luminous. That would soften the crisis. But even in softened form, the core tension remains. The universe grew up fast, faster than comfortable. And fast growth implies intense initial conditions, which leads to one final layer, the cosmic horizon. There is a limit to how far we can see. Light has finite speed. The observable universe is not the whole universe. It's the portion whose light has reached us since the Big Bang. Beyond that horizon, we don't know. If early structure formed rapidly here in our observable patch, what about beyond? Inflation predicts that our visible universe is just a tiny region of a much larger whole, potentially infinite, potentially structured differently elsewhere. If quantum fluctuations seeded galaxies here, they seeded them everywhere. But what if the amplitude varied slightly beyond our horizon? What if our patch is statistically unusual? Webb cannot answer that. But by refining how typical or atypical early structure appears, it sharpens the statistical frame. And here is the humbling truth. Every image Webb sends back is both revelation and reminder. Revelation of ancient light. Reminder that we are interpreting shadows of processes we cannot directly witness. We reconstruct, we simulate, we theorize, but we are always a step removed. The photons arriving at Webb's mirrors began their journey before Earth existed. They crossed expanding space for 13 billion years. They carry encoded information from a time when nothing resembling humanity was even possible. And yet now, in a control room on Earth, we decode them. That alone is staggering. Atoms that were forged in early supernova now sit inside your brain, using mathematics to interpret light from their ancestors. There is continuity there, not mystical, physical. The early galaxies Webb observes produced heavy elements. Those elements enriched later generations of stars, eventually forming planetary systems, eventually forming chemistry, eventually forming observers. So when we look at early structure and feel surprise, it is the universe becoming self-aware of its own origins, through us. And that reframes the entire shock. Maybe the real disturbance isn't that galaxies formed too early. It's that we assumed simplicity, that we underestimated how quickly complexity can ignite. The Big Bang may still stand. The timeline may be refined, not rewritten. But the psychological impact is undeniable. The beginning feels less empty, less naive, more fertile. And that changes how we think about everything that followed. Because if the universe was architecturally ambitious from the start, then its future may hold structures beyond our current imagination. Webb is not the final telescope. It is a beginning of a new era. Its data will be debated, models adjusted, some tensions resolved, others deepened. That is how science evolves. But the pattern is unmistakable. Every time we build an instrument capable of seeing deeper, reality becomes more intricate, not simpler. We thought the solar system was everything. It wasn't. We thought the Milky Way was everything. It wasn't. We thought early galaxies would be faint, fragile seedlings. They weren't. So here is the quiet ending. You live in a universe that, in its infancy, may have been more active, more structured, more explosive than we imagined. The night sky above you is not static. It is a time machine. And the deeper we look, the less certain the word beginning becomes. Because perhaps beginnings are not sharp lines. Perhaps they are gradients. Perhaps what we call the start was just a transition we haven't yet fully understood. James Webb looked too deep into space. What it found wasn't monsters. It found maturity where we expected infancy. And that subtle mismatch may be more revolutionary than any single discovery, because it whispers something unsettling. The universe did not hesitate. It built immediately. And if that is true, then the story of existence did not begin in darkness, slowly learning to glow. It began in a blaze of structure we are only now starting to comprehend. which means the deepest mystery was never just out there in distant galaxies, in our assumptions about how everything begins. And those assumptions are still evolving.